dual nature of matter and radiation. So here, if you take the radiation, that is electromagnetic radiation. So the electromagnetic radiation has some energy. This energy of electromagnetic radiation is given by E is equal to h nu. So this is proposed by Max Planck in 1900. So according to Max Planck's quantum theory, this is also called Max Planck's quantum theory. This electromagnetic radiation has energy in the form of energy packets, and each packet has energy of h nu, where this is called Planck's constant, and this is the frequency of radiation emitted by a body, or that electromagnetic radiation. And Planck's constant value 6.62 into 10 power minus 34 joule second. And he introduced the concept of energy packets. So this energy packets, that means radiation consists of small energy packets here. So according to that energy packet, nowadays we are calling these energy packets as, these are also known as photons. Now we call it as photons. So what is the energy of this electromagnetic radiation? So this electromagnetic radiation consists of small photons. These are not particles or waves, these are just energy. So energy of each one is equal to h nu. If there are n photons, the total energy of these n photons is given by E into n into h nu. So this is nothing but energy of electromagnetic radiation is quantized, where n can be 1, 2, 3, 4 and so on. Just like in electrostatic, we studied this as Q is equal to Ne. The total charge on a body is equal to integral multiple of charge of the electron. Similarly, the energy of electromagnetic radiation is equal to one integer into h into nu, where nu is the frequency. So this is the energy of one photon or one energy packet. So here we can say that according to Max Planck's quantum theory, electromagnetic radiation has some energy, and the energy of the electromagnetic radiation is also quantized, just like quantization of charge. Energy of electromagnetic radiation is quantized. Now, what are these photons and what are the properties of photon? Now we will discuss about this one. Properties of photons. The first one, photons cannot exist at rest. They always move with the speed of light in straight line. So photons always moves in straight line, and the speed of these photons is always equal to speed of the light, which is equal to 3 into 10 power 8 meter per second. If there is a photon, generally it does not exist at rest. If a photon exists at rest, compulsory its mass must be 0. So what is the meaning of this statement? Photon cannot be at rest. It cannot be at rest. The second one, photons do not deflect either in electric field or magnetic field. Let us say if photons are, these are energy packets, remember, these photons are traveling through an electric field here. This is the electric field. So these photons will travel without deflecting through this one, because protons are electrically neutral. If they are positively charged, then it might have traveled along the direction of the electric field. If they are negative charged particles or negative charged this one, then they might have traveled in the opposite direction to the electric field. But here they are traveling in a straight line. That means they are electrically neutral. The same thing can be seen in case of a magnetic field also. If they are allowed to pass through a magnetic field also, they are moving in a straight line path only. So first point, photons moves in a straight line path with the speed of this one, and they cannot be at rest. And second one, as they are electrically neutral, they won't deflect either in electric or magnetic field. Third one, energy of photon is directly proportional to the frequency. So E directly proportional to frequency nu, or E is equal to h nu. Suppose if you take a material medium here, two different material mediums, when the photons are incident on this one, now some of these photons will reflect and some photons will refract through the surface, just like in case of light only. Here, that means the photons obeys laws of reflection and refraction. That also you can add here. Photons obey laws of reflection as well as laws of refraction. So from this we can write, whenever these photons incident on this one, the energy of this photon depends only on the frequency. So these photons are, let us say, coming from a bulb, a source here, let us say bulb. So photons are coming here. Whenever the source changes, then only frequency changes. Otherwise energy remains constant as the frequency of the source remains constant. Here, as they are traveling, let us say this is through air. When they travel through water, what happens to the frequency? Frequency never changes when the radiation travels from one medium to another medium. So frequency only depends on source only, nature of the source. So frequency remains constant when radiation travels from one medium to another medium. So here, let us say frequency of the radiation in air is mu, frequency of radiation in water also mu. So this will not change. But we know that whenever radiation moves from one medium to another medium, its velocity changes. Here in air, the speed of the radiation is 3 into 10 power 8, but in water, speed is less. So here I am writing this as V in air and this is V in medium. V in air greater than V in medium. So when the radiation travels from rarer to denser medium, velocity decreases. So here this is, I will write this V1, this let me write it as V2. So V1 is more, V2 is less. But we know that velocity is equal to frequency into wavelength. As the frequency is not changing either in this medium or in this medium, so this frequency never changes. But velocity decreasing when it travels from one medium to another medium. So we can say that wavelength of the radiation in the rarer medium is more here. Here lambda is more. Here lambda 2 is less here. So wavelength will decrease in this case. The energy of the radiation is given by E is equal to h nu. But according to Einstein's mass energy relation, this can also be written as mc square. So from this, h nu is equal to mc square. And what is this frequency? Suppose if the radiation is traveling through air, so in air we can write h into mu is equal to c is equal to mu lambda, or mu is equal to c by lambda in air, which is equal to mc square. You can cancel this and so h by lambda will be mc here. This is equation 1. Similarly, in any other medium, the same equation can be written as h nu is equal to mc square. So h into, now mu is equal to v by lambda, which is equal to mc square. So from this we can write h is equal to, mass of this particle can be given as, mass of the photon is given as hv by lambda c square. This is the mass of photon when it is traveling through a medium. But when it is traveling through air, what is the mass of photon? So from this we can write m is equal to h by c lambda. So from this we can write, you can see this mass of photon in air is h by c lambda, whereas mass of photon in a medium is hv by lambda c square. So whenever medium changes, mass of the photon also changes. Now fourth point, photons carry momentum. So what is this momentum? We know that momentum is nothing but, here I am denoting this momentum as a small p here, which is equal to mass of the photon into speed of the photon. When the medium is not mentioned, let me take the speed of light, which is equal to 3 into 10 power 8. So this can be written as, we know in air, the mass of the photon is given by h by c lambda. So in place of m, I am going to write h by c lambda into c here. The c get cancelled. So momentum is given by h by lambda. So here also momentum is a constant by wavelength. Whenever the wavelength changes, the momentum changes. Intensity of radiation depends on the number of photons in it. Suppose if you take a source of electromagnetic radiation, so this source will emit a radiation in all possible directions in a straight line. So the intensity of the light here, intensity of this radiation depends upon the number of photons emitted by it, not in it, this is emitted by it. Now we know that intensity is given by energy emitted by a source in unit time per unit area, in unit time, in unit area. So intensity can be given as E by T into A here. If the source emits only one photon, energy will be E is equal to h nu. If the source is emitting n photons per second, let us it is emitting n photons per second, then the intensity is given by Ne by Ta. Here what is this n by T? This is the rate at which a source emits photons per second. So this is called photons emitted per unit time, photons emitted by per unit time. So n by T can be given as Ia by E here. But what is this n by T value in other terms? This can be given as intensity into area by E is equal to hc by lambda. Let us say the power of this source is P here, because bulb power will be given as 30 watts, 40 watts, 50 watts, 60 watts. When the power is given, power is nothing but energy emitted per unit time. This power, in place of this one, you can write this energy is equal to h nu. If they are emitting n photons, this will become n h nu by T. So in this case, what we can write, the power is equal to, be careful while writing the momentum and the power in this one. Momentum we are denoting with the small p, power we are denoting with the capital P here. So this will be n by T into h, mu is equal to c by lambda. So from this also we can write n by T can be written as the number of photons emitted by a source is given by power of the source into wavelength by hc, that is P lambda by hc. So this is the photon rate. Photon rate means photons emitted by a source in unit time. So this is one expression, and this is another expression where we can use this. We can use when the power is given. This we can use when the intensity of the light is given. So from this we can say area is constant, h constant, speed of light constant, wavelength constant. So intensity directly proportional to photon rate, number of photons emitted per unit time. We will solve a problem. There is a bulb of 100 watts and emitting radiation of 500 nanometers. So if the power of the bulb is 100 watts and wavelength of the radiation emitted by this one is 500 nanometers, what are the number of photons emitted per unit time? So this is also called photon rate. Rate of photons emitted by the source of this much power. And we know that as power is given, power is nothing but energy emitted per unit time. If it is emitting one photon, this is E by T. For n photon, Ne by T. So power can be given as n by T into energy is equal to hc by lambda. Now I want this n by T, so this n by T can be written as power of the source into wavelength of the source by hc. So by using this expression we can find out the photon rate or the number of photons emitted by this source per unit time. Remember students, the power is given as 100 watts and the wavelength is 500 nanometers. So this is 500 into 10 power minus 9 by. What is H value and C value? We know the Planck's constant value 6.62 into 10 power minus 34 into C will be 3 into 10 power 8. So if you calculate this value by using this one, and this is a big calculation, but 6.6 into 3 will be around 19.8. So nearly you take this as, nearly you can take this as 20. So this will become 5 into 10 power minus 5 by, this multiplication is nearly 20 into 10 power minus 34 into 8 minus 26. So 5 ones, so 5 fours. This is 1 by 4 into 10 power 26 minus 1, 21. 1 by 4 is 0.25 into 10 power 21 or 2.5 into 10 power 20. These are the number of photons emitted per unit time here. This is equal to 2.5 into 10 power 20. Radiation pressure. Let us say some photons are incident on a perfectly reflecting surface. So the surface which reflects all these photons perfectly is called perfectly reflecting surface. Let us say some photons are incidenting on this one and they are reflecting in the opposite direction. So while moving in this direction, momentum is P, while coming back the momentum is P only. The only thing is this momentum, if you take one of the momentum as positive, this momentum will become negative. So what is the change in momentum? Change in momentum from a perfectly reflecting surface is given by delta P, which is equal to P minus P. So change in momentum will become 2P equation 1. But we know that the momentum of a photon is given by P is equal to H by lambda. So this change in momentum can also be written as 2 into H by lambda. So change in momentum is given by 2 into H by lambda is equal to, we know that C is equal to mu lambda or lambda is equal to C by mu. So this is the change in momentum for a single photon. So this is for a single photon. If there are n photons that are striking this one, let us say n photons are incident on that perfectly reflecting surface. For n photons we can write intensity. The number of photons striking a surface per unit time per unit area is called intensity. So here intensity is given by n photons, that is n times the energy incident. E is the energy of one photon, Ng is the energy of n photons incident per unit time per unit area. So this can also be written as n by T into what is the energy of each photon, which is given by h nu by T. So from this equation we can write this n by T as, that is number of photons striking per unit time on the surface is given by intensity of radiation into area on which these are incidenting here, because n photons are striking now. So that area we have to consider Ia by h nu. So this is equation 3 here. So this is the change in momentum for a single photon. Change in momentum for single photon. Now for, if there are n photons, so how many photons are striking per unit time? That is intensity of the entire radiation into area on which it is incident by h into frequency of that radiation. So now what is the change in momentum? The rate of change in momentum. Rate of change in momentum is given by This is delta P by delta T. This is for one photon. If there are n photons, this can be written as n into delta P by delta T, or simply n by T into change in momentum. So this is, what is n by T? N by T is nothing but Ia by h nu. So I am going to write Ia by h nu into, what is the change in momentum for a perfectly reflecting surface? This is going to be 2 h nu by c here. You can cancel this h nu and h nu. So the rate of change in momentum according to Newton's second law, this is nothing but the force acting on this one. So this force is called a radiation force here. The radiation force acting on this perfectly reflecting surface is given by F is equal to Ia 2Ia by C here. This is the radiation force. But we are talking about radiation pressure. We know that pressure is equal to force by area. Radiation pressure is nothing but radiation force acting on unit area of that surface. So now I am going to write this as radiation pressure P is equal, this force by area, which is equal to 2I by C here. So this is the radiation pressure. Suppose instead of a perfectly reflecting surface, let us say if you take one perfect black body here, this is a black body. Black body is a substance which absorbs all the radiations incident on it. So on a perfect black body, when the radiation incidents, this momentum will be P, and the reflected momentum will become 0 as it is a perfectly black body. It absorbs all the radiations incident on it. Then what happens to these formulas? Change in momentum will be this momentum minus 0, which is equal to P, and the change in momentum for unit time, what we call it as force. This force will become half of this value because all other quantities are same. Here change in momentum is P, which is equal to h by lambda, that equal to h nu by C here. This is the change in momentum. So F is equal to dP by dt into n photons. This can be written as h nu by C into this n by T is nothing but Ia by h nu. So this is Ia by h nu. H nu cancel. So radiation force is equal to Ia by C. But what is the radiation pressure for a perfect black body? So radiation pressure, I am not writing P again. Why? Because already we are using small phi for momentum, capital Phi per power of the source. That's why I am just writing radiation pressure is given by force by area. So this is equal to I by C here for a perfectly black body. For a reflecting body, 2 times of I by C. For perfect black body or absorbing surface, this will become I by C. Radiation pressure is for a perfectly reflected surface. The change in momentum is this much. Radiation force, this change in momentum for unit time is this much, 2I SPC. And radiation pressure is given by F by A is equal to 2I by C. If the entire radiation is reflected from the surface, so this is momentum P. If the entire energy is reflected here, we will write 2I by C. If only 0% of the light is incident on this one, that means 0% light is emerging, then the momentum will become I by C. But in this problem, you see a monochromatic beam of wavelength this much, incident normally upon a surface, produce a pressure of this much. So this is the radiation pressure produced on it. Now, if 25% of the light incident is only reflecting, so out of 100%, this is 100% light incident on this one, but only 20% of the light is emerging out from the surface. So out of 100%, only 25% is coming out. So in the previous case, this is 100% and 100% light is reflecting. So you will get 2 here. That is 100% plus 100%. that is 200%, that is 200 by 100. So you will get a 2 here in this formula. Here, out of 100%, 0% light is coming back. So this is total 100% plus 0%, that is equal to 100% only. That is 100 by 100. So 1. So I got 1 here. But in this particular problem, there is a surface on which incident, some radiation is incidenting on this one. Let me take it as 100%. But out of this 100%, only 25% of the light is reflecting. So now after this, only 25% of the light is reflecting. So based on these two, here I got 2 into I by C, here I got 1 into I by C, but here some radiation is reflecting back. So this is 100% plus 25%, which is equal to 125%. So if you divide with this one, you will get 125 by 100, which is equal to 1.25. So what is the radiation pressure now? The radiation pressure is given by, in this problem, directly I can write 1.25 I by C here. So we need to use this formula. So the radiation pressure in this problem, I am going to write the solution. Radiation pressure is given by 1.25 I by C. So the radiation pressure is given as 5 into 10 power minus 7 is equal 1.25 can be written as pi by 4 here, 5 by 4. Intensity of light we don't know, and C we know 3 into 10 power 8. So from this we can find out the intensity of light that is striking the surface. So intensity is given by, now I am finding intensity I is equal, multiply this one, 5 4s are 20, 23s are 60 into 10 power 8 minus 1, 10 by 5 here. So this is the intensity of this one, 5 1s, 5 12s, this is 120 as it is intensity, that is energy per unit time per unit area, watt per meter square. So now I got the intensity of the light in this problem. Now to find out the number of photons here, so I got the intensity. We know that intensity is equal number of photons incidence per unit time into energy by area in this problem. So here, as we got the intensity, we need to find number of photons falling on the surface. So I need this n by t, and this is for unit area only. So falling on unit area, so I can take this as a 1 here. So the number of photons incident for this is also per 1 second here. They are asking to find out 1 second. So this number of photons is given by I by E here. So what is the intensity of the radiation? It is given as 120. And what is the energy of the radiation? We know the wavelength of the radiation. From this we can find out energy is equal to h nu or hc by lambda. So we know this h value, c value, lambda value. So energy of the radiation is 6.6 into 10 power minus 34 into C3 into 10 power 8 by, this is 4900 angstroms. So this is 4.9 into 10 power minus 7. So now we have to do this 6.6 into 3 by 4.9, 10 power minus 34, this minus 7, 10 power minus 27, this will become 10 power minus 19. So 6.6 into 3, nearly 20. This 4.9, nearly 5. So 20 by 5 will be 4 into 10 power minus 19. This is the energy of each photon. So divide this total intensity with the energy of each photon, which is equal to 4 into 10 power minus 19. 4 1s, so 4 30s. So the number of photons incident per second per unit area is given by 30 into 10 power minus plus 19. So this is 30 into plus 19 or 3 into 10 power 20. So this many number of photons are incident on this one. Out of this only 25% are reflecting back. If the radiation incident on a perfectly reflected surface, not normally, let us say it incident at an angle here. Now let us say this angle is theta, then this is can be resolved into theta here. This momentum is P. This momentum will be P cos theta. This will be P sin theta. As it is completely reflecting, so this momentum is also equal to P cos theta. So change in momentum is P cos theta minus of minus P cos theta, which is equal to 2P cos theta equation 1. Similarly, in this case, when we are finding this change in momentum, what is the intensity of the light on this surface? The intensity of light here, the n into h nu by t into the area component or the area vector, which is perpendicular to this radiation. So if it is P cos theta, you can write this one. Area vector is A cos theta for this one. So from this we can write the change in rate of change in momentum is delta P into n by t. So here we have n by t. This is 2P cos theta into n by t can be written as Ia cos theta by h nu. So this 2P cos theta, which is nothing but, we know this as equal to 2 into P is equal to h by lambda into cos theta, or 2 into h lambda is equal to c by nu cos theta. So this I am going to write as equation 1. And if you substitute this value here, this in place of delta P you can write 2P cos theta or 2h nu cos theta by c into Ia cos theta by h nu. H nu get cancelled. This will become 2Ia by c cos square theta. This is the radiation force. The radiation pressure is given by force by area, which is equal to 2I by c cos square theta. For normal incidence, we know that theta will be 0 and cos 0 is equal to 1. You will get this equation 2I by c for radiation pressure. Now, suppose if the surface is not a perfect black body, perfect surface, let us say this is a black body. Now the radiation, let us say incident at an angle theta with the vertical here. So this can be resolved into two components. Here this is theta, this is P cos theta, this is P sin theta, where P is equal to h by lambda or h by c mu sin theta. This is h nu by c cos theta here. So in this case what happens? Now I am going to find out this radiation, which is a normal radiation. So we have two types of radiation pressures here. Normal radiation pressure. For normal radiation pressure, we have the same equation. As it is a perfect black body, there is no reflected light here. So from this we can write the same expression, but this force, normal to the black body is given by here. This is a 2Ia by c cos theta, but this will become Ia by c cos square theta only. But here, if you take this momentum which is parallel to this one, this will also produce some force as well as pressure on this one. This is the normal radiation pressure, which is given by I by c cos square theta. These are the normal forces and pressure normally to the surface, but parallel to the surface, as it is the momentum acting parallel to the body. Here we can write the change in momentum is nothing but the this one only, as no radiation is incident on this one. Now the number of photons per unit time, that is given by Ia cos theta by h nu. So now the force, which is given by rate of change of momentum, that is delta P into n by t, that is h nu sin theta by c into Ia cos theta by h nu cancel. So this is called as it is a tangential surface, we call it as a shear force, shear radiation force, which is given by I into area by C into sin theta into cos theta. So this is the shear force acting on a perfectly black body or perfectly absorbed surface, and the shear pressure or tangential pressure, radiation pressure is given by force by area, so which is equal to I by C sin theta into cos theta. According to Louis de Broglie, as the radiations exhibit dual nature, that is wave nature as well as particle nature. Similarly, wave is also associated with every moving particle. These waves which are associated with the moving particle are known as de Broglie waves as well as matter waves. That means electron actually considered as a particle will have the particle nature as well as this has a wave nature, and this is confirmed by Davison and Germer experiment. So this was proposed by de Broglie but confirmed by Davison and Germer here. Now in this case, let us say for a photon we know that energy is equal to h nu, which is equal to hc by lambda, but this is equation 1. But the energy of any mass, that is mass energy relation, gives that whenever a particle moves with a speed of light, this energy is given by mc square, the famous mass energy relation given by Einstein. From these two equations we can write hc by lambda is equal mc square. This is c and c get cancelled. So from this we can write h by lambda is equal, this is mass into velocity, which is called momentum. So what is the momentum of photon? That is h by lambda. But here this wavelength, which is having this wavelength when it is traveling the speed of light, we call it as a de Broglie wavelength. So I am going to write de Broglie wavelength for a photon is given by lambda is equal to h by p, where p is equal to mc, that is h by mc. This is the de Broglie wavelength of a photon. Suppose if a particle is moving, a particle of mass m moving with a velocity v, then what is the de Broglie wavelength? Because every particle will behave as a wave, and wave will have some wavelength, and this wavelength of a particle moving with velocity v of mass m is given by, we know that lambda can be written as h by p only. Here we can write lambda is equal to h by p, which is equal to h by mv. This is the de Broglie wavelength of a proton. Wavelength of a particle, not proton, particle. De Broglie wavelength of a particle is given by, for a particle is given by lambda is equal to h by p, which is also given by lambda is equal to h by mv. But we know that the kinetic energy of a particle is given by p square by 2m. So p square is equal to 2m ke or root over 2m ke. So the de Broglie wavelength of a particle of mass m moving with velocity v can also be written as h by p, can be written as root over 2m ke, and this as the particle of mass m moving with a velocity v, so it has to move between 2 points which are separated by a potential v here. This is a potential difference between these two. Due to this, particle attains some kinetic energy. So we know that work done on this charged particle that is VQ is equal half mv square. This is the work done, which is equal to change in kinetic energy. Initially, let us say this is at rest. Now it got velocity v here. So VQ is equal to half mv square. So from this we can write 2VQ is equal or VQ is equal to KE here. So in place of KE you can write VQ also. So wavelength is equal to h by root over 2m into VQ. So these are the different formulas to find out the de Broglie wavelength of a particle of mass m moving with a velocity v, and it is traveling between 2 points of potential difference v. So these are all the equations. From this expression, lambda is equal to h by root over 2m VQ. If any charged particle is allowed to pass between 2 points having a potential difference of v, let us say, let me take it as a proton first. For electron first, for electron, what is the de Broglie wavelength? For electron, the de Broglie wavelength is given by h by root over 2m VQ. Here the constant values, h is a constant which is equal to 6.6 into 10 power minus 34. M is mass of electron which is equal to 9.1 into 10 minus 31. Q is the charge of electron which is equal to 1.6 into 10 minus 19. And if you substitute all these values, you will get 12.27 by root v angstroms. So whenever a problem is given based on electron, if the potential is given, directly you can write 12.27 by root v angstroms. So instead of substituting all these values, calculating all these values, root v remains as root v only. Suppose if potential applied is 50 volts, so what is the de Broglie wavelength of the electron? 12.27 by root 50. Root 50 is nearly root 49, which is equal to 7. So 7 in 12.27 by 7, you will get the de Broglie wavelength for electron. Similarly, for a proton, lambda proton is given by, once again, h value is 6.6 into 34, 2, but mass will be 1.67 into 10 minus 27, charge remains as 1.619. So if you substitute all these values, once again you will get 0.286 by root v, but here you will get, you will not get the wavelength in meters, you will get a wavelength in angstroms. Similarly, for a deuteron here, lambda deuteron is given by, substituting all these values, you will get 0.202 by root v angstroms. Similarly, for alpha particle, for an alpha particle, this lambda alpha is given by half of this value, which is equal to 0.101 by root v angstroms. So we need to remember these 4 formulas for de Broglie wavelength of light, as well as these 4 values for electron, proton, deuteron and alpha particle. So after observing this one, it is clear that as the numerator is the same for all these particles, so which particle has the highest de Broglie wavelength? Very simple, 12.27 is greater than 0.286 and greater than 202 and greater than 0.101. So for the same wavelength range, we can write lambda electron greater than lambda proton greater than lambda deuteron greater than lambda alpha particle if the potential is same. But sometimes they may give different velocities, different potentials, then we have to compare by using these formulas.